Plastic trim fade is one of the most common long-term appearance complaints on vehicles. Yet, it is often misunderstood. Unlike metal panels, plastic substrates have different thermal expansion coefficients, lower surface energy, and are inherently more sensitive to ultraviolet, UV, radiation, and environmental stressors. From an OEM durability perspective, fading of plastic trim is not purely cosmetic. It is a reflection of polymer chain degradation, additive depletion, and surface oxidation that compromise both appearance and protective function. Plastic substrates are chemically and mechanically distinct from steel or aluminum. Polypropylene ABS and TPO blends are widely used for exterior trim due to their lightweight and impact resistance, but their surfaces are less receptive to standard coating chemistries. Adhesion promoters and primer surfacers are required to create a robust interface, and even small deviations in application can significantly influence long-term performance. Unlike metal, plastics expand and contract more with temperature, introducing cyclic stress that accelerates surface degradation. UV radiation is the primary driver of fade. Plastics absorb UV differently from metals and often transmit energy directly to the coating layer, causing chain scission, oxidation, and additive depletion at a faster rate. Polymeric dyes and pigments in the coating absorb light energy, converting some to heat, which increases local substrate temperature and accelerates degradation. Unlike clear coat over base coat systems, plastic trims often rely on a single-layer topcoat or pigmented coating to deliver both color and protection, making them more vulnerable to photochemical attack. Additives are critical to controlling fade. HALS hinder amine light stabilizers, interrupt radical chain reactions caused by UV, while UV absorbers convert high-energy photons into harmless heat. Surface waxes and slip additives reduce micro-roughness formation and maintain hydrophobicity. However, all these additives are consumed over time. Migration to the surface initially protects the top layer, but repeated environmental exposure, rain, abrasion, temperature cycles, depletes these additives, exposing the underlying polymer to degradation. Thermal expansion mismatch between the plastic substrate and coating amplifies stress. On hot days, plastic trim can reach temperatures significantly higher than painted metal panels. Expansion and contraction cycles create microstrains that promote crazing, microcracking, and surface roughness. These microstructural changes scatter light and reduce color vibrancy, which is perceived by the customer as fading. Edge and corner regions, especially around mirrors, grills, and body side moldings, are most vulnerable due to geometric stress concentration. Environmental contaminants further accelerate fade. Industrial fallout, road salts, and hydrocarbons chemically interact with the surface, oxidizing pigments and polymers. High humidity or acidic rain exacerbates surface oxidation. Water ingress at seams or along edges can hydrolyze polymer chains, weakening adhesion and allowing dirt to anchor more readily, which both reduces visual gloss and amplifies perceived fade. Curing and coating formulation are pivotal. Undercured coatings are softer, allowing contaminants to penetrate and increasing early additive depletion. Overcured coatings resist chemical penetration but are brittle, making them prone to microcracking under thermal stress. OEM bake profiles and formulation optimization are validated for specific plastic substrates because mechanical and chemical tolerances differ from metal panels. Even slight deviations in film thickness or solvent balance can have outsized effects on long-term fade resistance. Detection and evaluation of fade rely on colorimetry, gloss measurement, and accelerated weathering tests. Xenon arc testing simulates years of outdoor exposure in weeks, allowing engineers to evaluate additive performance, pigment stability, and substrate coating interactions. Observing both initial color retention and long-term degradation patterns provides insight into failure mechanisms that might not be visually apparent until months or years of service. From a troubleshooting perspective, fade complaints are analyzed by substrate type, coating chemistry, and environmental exposure history. Engineers consider UV exposure patterns, temperature extremes, and local chemical attack from contaminants. Adjustments in additive load, film thickness, and surface pretreatment are common corrective strategies. However, no plant-level adjustment can fully compensate for inherent polymer limitations without redesigning the coating system or substrate treatment. Plastic trim fade is a complex interaction of physics, chemistry, and materials engineering. Success requires understanding the substrate, anticipating environmental stresses, selecting the correct additives, optimizing crosslink density, and controlling cure. OEM coatings are designed to minimize visual degradation over the intended service life while maintaining color vibrancy, gloss, and resistance to environmental attack. If you've noticed dull or faded plastic trim, discoloration, or early loss of color vibrancy, leave your questions in the comments. Upcoming episodes will continue exploring substrate-specific durability challenges, environmental effects, and OEM-level strategies to maintain appearance over time.